Hello, we are going to see RADIAL basis function networks today. We have already seen multi-layer perceptron, and its applications and its algorithm. We have seen how to achieve the convergence is what we have seen. What are the various adjustment parameters we have already seen. So today we are going to see another important and interesting neural network, and that is called as a RADIAL basis function network. So what we are going to see today is the concept of RBFN and the basis on which it is relying on, which is called as the Gaussian theorem, the architecture, the discriminant functions, XOR problem, solution to XOR problem using RBFN, the actual RBFN algorithm, K means clustering, followed by some demo, and finally with the comparison and applications of MLP and RBFN. So what is the concept of RBFN? We can see that MLP, that multi-layer perceptron, is can be considered as a stochastic approximation approach, but we can also see it as a surface fitting consideration. We have already seen the linear regression, and we have seen that we can have regression, non-linear regression also possible with the help of the multi-layer neural network, that is MLP, multi-layer perceptron, and it can be called as a surface fitting there if it is extended into the higher dimensions. Now why MLP succeeds? Because of the in-between mapping done by the hidden layer. We have already seen why this happens. For a problem where we cannot pass a hyperplane for separation, that is non-linearly separable problems, but we may be able to pass some hypersphere or hyperquadratic quadric, that is a multidimensional surface. So therefore, given a non-linearly separable problem, our task is to determine a hypersurface that can classify properly, which is a surface fitting problem in multidimensional space, and it is the essence of the RADIAL basis function network. Why it is called RBF? Because it is RADIAL basis function, a function which depends only on the radial distance from the center or the point. We start with the Gaussian theorem. What does Gaussian theorem say? It states that a pattern classification problem cast in higher dimensional space is more likely to be linearly separable than in low dimensional space. It simply means that if I map lower dimensional problem into a higher dimensional one. Now this is something which is a little bit odd, because we said that we want to decrease the number of dimensions, but here Gaussian says exactly the reverse, and that is if we increase the number of dimensions, it is likely that in the higher dimensional space the problem becomes linearly separable, and then we can use our conventional algorithms. A simple gradient descent algorithm can be used over there to classify or separate out or find out the hyper plane between the two classes. Now consider a set H of n patterns, x1, x2 and xn. All these are vectors. Each vector can be assigned to any of the two classes. Say that it's a two class problem, h1 or h2. If you have family of surfaces wherein at least one surface separates the two classes, then we say that the set H is separable with respect to that family of surfaces. As we can see that there can be infinitely large number of lines, if you remember the previous session. So it's actually a family of lines. It's not only a single line which can separate. In a similar way, we can have, so just like the family of lines, so many number of lines passing through which can be used for separation, we can have the surface or the family of surfaces. So let us say x bar, that is your vector, input vector, has got m naught number of dimensions. For each x which is belonging to the set H, we define a vector made of set of real valued functions, which we call as the discriminant functions here. Now look at the thing over here, that for every m0 dimensions, I mean it has got m0 dimensions, and we are actually having, we will define a vector phi, which is a real valued function. Phi is a real valued function where I goes from 1 to m1, that is m1 number of real value functions. These are the hidden layer functions, so that the input vector gets transformed. So I am actually casting this particular vector into so many m1 number of let us say values. So actually what I am doing is I am mapping from m0 to m1. Okay, so each vector goes into rather creates m1 different values. So in fact what I am doing is I am increasing the number of, I am changing the number of dimensions here. So the space is spanned by the set of hidden functions, that is phi I, which is a function of the vector, or which operates on the vector. I goes from R1 to m1, which is the hidden space or the feature space. So I am actually increasing the number of dimensions, projecting the vector which is m0 dimensions into so many m1 different values. Okay, so we are mapping m0 dimension inputs to m1 dimension hidden space. So a dichotomy h1 h2 is phi separable if there exists one m1 dimensional vector such that we have already seen weight into that particular value. If it is greater than 0, it belongs to, let us say, h1. If it is less than 0, it belongs to h2, just like what we have done in case of the single neuron. So the hyperplane, which is actually defined just like the weight vector was defining, the weight was defining weight, and the biases were defining the slope of the line in the previous cases. Just like in this case the hyperplane, now you are having a hyperplane, so which is nothing but this W transpose multiplied by the discriminant function equal to 0. So this is an equation which is actually the separating function. So we have linearly separable, we have hyperspherically separable, and we have quadrically separable. So many of the problems will lie in this particular category. So if x1, x2, xn are independently chosen patterns and there are large number of dichotomies but only a few are separable, studied the probabilities of those dichotomies which are separable, and assuming all possible dichotomies are equiprobable, it says that the probability p n m1, that is denotes the probability that a particular dichotomy picked at random is phi separable and is given by Cover's theorem as p n comma m1, which is half of that of half to the power n minus 1, summing all m from 0 to mi minus 1. What is this? This is a combination. Okay, so if mi is a very high, if you make mi very high, then the probability is closer to 1. This is the gist basically, and it says that, and that is the reason why we say that if we make higher dimensions, if we project into higher dimensions, the probability of having a phi separability is linearly separable classes is very high. Okay, so this is basically the Cover's theorem. It can very easily be visualized by a very simple example, the XOR problem. Now XOR problem we have already seen in 2D space. Now if I project it in 3D space, for example, then you can see here that I can pass a single plane over here and separate these two objects or these 2 points. Okay, so it's very simple way of describing the Cover's theorem. Of course, we are here in this case what we have done is we have simply projected the 2D space 2D problem into a 3D problem, increase the number of dimensions, and here it becomes linearly separable actually according to the Cover's theorem. Let us see the RBFN architecture. So RBFNs have hidden units which provide a set of functions which form the basis. Now these are the basis functions which actually map from the input space to the hidden layer space of higher dimensions. So hidden neurons provide the basis functions, hence the name RADIAL basis function networks. Basic form of this consists of 3 layers: input layer, which is the source nodes, only one hidden layer. So here in this case we have only one hidden layer. In case of MLP we can have more than one hidden layers. So this hidden layer which does the non-linear transformation or mapping, where hidden space dimensionality is higher than input space. So we have already seen this is in correlation with the Cover's theorem. Output layer supplies the response. We already know this. This is the typical RBFN network. As you can see, x1, x2, this is one vector, this is one input or exemplar as we have already said, and we have in this case now these are the centers or cluster centers, as we'll see later on. So what we do is actually we project this n dimensional vector into m different values or m different centers, and simply find out. So we have these discriminant functions here. So what we do is we find out the Euclidean distance. Okay, so this becomes the argument for this function, and correspondingly whatever are the values generated we have over here in this case. So what we do essentially is we simply find out the Euclidean distance with respect to these centers. These centers are, number of the centers is m, whereas the input vector has got a dimension n, and m is most of the times greater than n. We already have seen that. So what we do is we simply find out the Euclidean distance of this input vector, okay, with respect to these centers, right? And then what we do is we have cast, actually by doing that we cast this problem into m dimensional space. So n dimension to m dimension. You can see here we have these real valued functions phi 1 through phi m. So you get these m dimensional vectors as such as m dimensional vectors, and this now we can simply use our conventional neural networks or neurons over here, and we can just find out the values of the weights over here, the biases over here, and you are good to go. So looking at this equation, it is simply y is equal to f of x, which is equal to summation of I goes from 1 to m. Now since we are having m discriminant functions, and the weight multiplied by, now this is the real valued output. Okay, this is what we have actually cast, and this is nothing but the Euclidean distance between the center Ci and the input vector. That's it. So what are the various discriminant functions which are possible? One very popular discriminant function is the Gaussian function. As you can see, it is localized, that is if the distance goes on increasing, the value output goes on decreasing. So if increases, so it is localized. If r tends to infinity, the output value, the value of this function goes to 0. So this is one very popular discriminant function. Another choice may be a multi-quadrix. Now this is non-localized. Here in this case it is the reverse way. As r tends to infinity, phi r also tends to infinity. So this is called as a multi-quadrix. We have inverse multi-quadrix. This is also an important function. So, and just like your Gaussian function, it is also a localized function. That is, if r tends to infinity, if I go farther and farther from the center point, the value goes on decreasing, and finally at infinity the value will be 0. Now let us take a look at the solution to XOR problem using RBFN. So this is our XOR problem. Now I am using the unipolar outputs again here in this case. X1, X2. I am having the centers as C1 and C2. Now it need not necessarily go for the higher dimensional space. It can be the same dimension but with a different in different space altogether. Okay, so I am having two cluster centers here. Now the number of centers over here, C1, C2, these are the centers actually, and what I can do is I can have large number of such centers, but just for simplicity of this example I am just taking two centers over here. Okay, so x1, x2 is your input. Okay, c1, c2 are the centers, and then phi1 and phi2 are the two discriminant functions which create some real values over here, and then I can use it, our conventional gradient descent algorithm. Let us see how it happens. So we select the two phi functions, that is the discriminant functions with the parameters mu equal to 0, and that is the mean equal to 0, and the variance as square root of half. This actually for simplification purposes we have taken it. So phi r, which is e to the power minus r square by 2 sigma square, reduces to only e to the power minus r square because of this adjustment. And we arbitrarily select the centers as 0, 0 and 1, 1. Now we'll see later on how to find out these centers. Basically we will be able to make use of the k-means clustering algorithm to find out the cluster centers. But for the time being, let us say we select C1 as 0, 0 and C2 as 1, 1. In fact, what I can do is I can select any two exemplars themselves as the cluster centers, 0, 0 and 0, 1 in this case. So, or maybe 1, 1. So I can take any cluster centers here. The discriminant function phi1 now is e to the power minus of whatever is the argument, that is nothing but the Euclidean distance between the input vector and the cluster center. Alright, now please remember one thing, the cluster center is also in the same space. So naturally same dimensions, x also will have same dimensions as C1 obviously. Okay, so the inputs are x, the distance from the centers are r, and the outputs from the hidden units are phi. So with that we start with this. So when all the inputs are presented to the net, for specifically for x2, okay, we will calculate one and show, otherwise for x1 it is going to be 0. So you can see over here very clearly for x2, here in this case x2 is this one 0 1. So what I do is I was first of all find out r1 r2, that is distance of this vector s, this is the vector x2, this is the vector capital X2. Okay, so I am showing the calculation for this particular exemplar. So if I calculate r1 turns out to be 1, r2 it turns out also to be equal to 1. So this r1 r2 is equal to, r1 is equal to 1, r2 is equal to 1. Now calculating the discriminant values, that is it turns out to be minus 0.3679 for both the cases. Okay, and now if I calculate the same things for all of them, my new values, these are my new values, which comes out to be 1.10, phi1 is 1, phi2 is 0.1. So actually I am mapping from x1 x2 to phi1 phi2 space, and let us look at how it looks like. So this is phi1 phi2 space, and the mapping that has taken place has given me this results. As you can see that one particular combination happens to be overlapping. Okay, these two actually happen to be the same points. Now in this particular space it is very easy for me to classify them, separate them out by using a single straight line. A single straight line simply means a single neuron. We already have seen that. So you can do that very easily with various different methods. One is directly, what I can do is I can find out the inverse, solve the equation, this particular equation I can solve. Phi, these are matrices, phi into w is equal to d. So this is phi, this is w, and this is d. D is the target. I am supposed to find out w1, w2 and w0. W0 happens to be the bias term. So naturally this is input x1, x2 and the input bias term, where the input is always equal to 1. So this matrix multiplication gives me, so I am supposed to find out this. Now I can solve this using two different methods. One is I can directly find out an inverse. Using the inverse I can find out w using a pseudo inverse, as a matter of fact. Why? Because this is not a square matrix, and square matrix, the inverse of a non-square matrix does not exist. But we can find out using what is called as a pseudo inverse. So this is actually the formula for pseudo inverse. So phi plus is the pseudo inverse. So how do you find out the pseudo inverse? Take that matrix, transpose of that matrix, post multiplied by the same matrix, invert it, okay, and again post multiplied by transpose of the matrix to get a inverse, pseudo inverse it is called as. Now if I simply solve this equation, I can get w. So I am using the same kind of thing here in this case. So solving this using pseudo inverse, I get w is equal to this particular matrix, minus 2.5 and so on and so forth. Okay, and finally to check the solution, I again implement, I again solve I again carry out the operation for this particular equation. This is matrix multiplication, and to get verify whether I get the same value for d, and you can see very well that it gives me the exact values for C. So this is a direct method. Now this was a very small problem, small in the sense the number of exemplars were very small. In most of the real life applications this won't work, because you may have a very large matrix over here. Okay, number of samples, number of exemplars can be hundreds. So the dimensionality of the matrix goes to 100 by 4, 100 by 5, and going for this kind of operation like the pseudo inverse of such a huge matrix, it's very computationally intensive. So normally these kinds of problems, very small kinds of matrices can be solved very easily using this method. Otherwise we make use of the gradient descent algorithm. Okay, so fixing the radius, that is the sigma. Okay, so this is usually done using the p nearest neighbor algorithm. Number p is chosen, and for each center the p nearest clusters are found. RMS distance, that is basically how do I select the value of sigma. In the previous case we have simplified it by saying that the sigma, that is the radius, okay, simply as we arbitrarily took it as 1 by 2, but it is not necessary that it will be the best value. So this particular equation gives you how to select the value of suitable value of sigma. This is the RBFN algorithm. Step number 1, get n, k, n, capital N, the feature vectors and their target vector. Input the number of iterations I, set I equal to 0, set m centers of RBFN as n exemplar vectors, MSE goal and learning rate alpha. Now remember that we are supposed to find out the cluster centers first. Cluster centers we had arbitrarily chosen because it was a very simple problem. Now here in this case we use an unsupervised learning, which is the k means clustering, to find the m number of cluster centers. Okay, so RBFN has got two parts. One is the unsupervised learning, because we don't know how many number of clusters we may ideally require. We just arbitrarily start with some number of clusters, which is number is higher than your dimensionality of the input vector, and then you compute the discriminant matrix and then start with the supervised learning. It is a simple gradient descent, that is a delta rule update we use, and compute the values of W and weight and the biases. Okay.